Hi, good day, everybody, wherever you are in the world. Welcome to today's webinar. Today's webinar is going to be on the AMF Annex 56, titled Methanol as Motor Fuel. We've got a list of 5 speakers lined up for today, and they will be speaking about the different elements that contribute to the totality of this report, which is on methanol as a motor fuel for different modes of mobility or transport. So we've got a long program lined up for everybody today. I'll just make a quick introduction. My name is Tim Chan. I'm the Manager for Government Relations and Business Development at Methanol Institute. I'm based in Singapore, and I'll be your moderator for today. So I'll take a short time to introduce today's webinar and also go through a couple of logistical issues before we quickly dive into the meat of today's topic. So as mentioned earlier, the AMF Annex 56 focuses on methanol as a motor fuel. It focuses on using methanol as a fuel in different types of mobility or different types of transport. And I will not talk too much about that because our presenters will be doing that shortly to come. As a quick introduction to the organization that I'm from the Methanol Institute. We are the global trade association for the methanol industry. We were formed in 1989. It's been slightly over 30 years right now. And now we have 4 offices around the world representing more than 40 companies who are methanol producers, methanol distributors, technology providers that might even deal with using methanol as a fuel. So as mentioned, I'm based in Singapore, but we have offices in Beijing, Brussels, Washington, DC, as well as where I'm from, which is Singapore. So quickly on the logistics, there are just a couple of issues that I would like to highlight. All participants, you're on mute, so you will not be able to raise your questions verbally, but there will be a questions tab on the control panel of GoToWebinar. If you click on the drop-down menu which says questions, you'd be able to type in your questions there, and there will be a question and answer session at the end of all presentations where we will try to address some of your questions in the time that we do have. Something else that I would like to highlight also in your control panel, there should be a drop-down tab called Handouts. In Handouts, if you click on it, you'd see 2 documents that are ready for download. Firstly, it will be for the first document would be today's webinars, the slides from today's webinar, and the second document would be the AMF Annex 56. So do feel free to download the documents from the GoToWebinar control panel, and I will not take up too much of your time right now. So let's start with introducing the first speaker, and we'll dive right into the meat of today's topic. So the first speaker I'd like to introduce is Niels Olof Nylund. He has a Doctor of Technology degree in Mechanical Engineering, and his current position is part-time senior advisor for engines and vehicles at VTT Technical Research Center of Finland. So without ado, Niels Olof, I will pass on controls to you, and you'd be able to proceed with your presentation.
Okay, thanks, Tim. So I have a 40-year experience with methanol as a motor fuel and a 30 years experience with IEA Advanced Motor Fuels Technology Collaboration Program. The current chairman, Jesper Schramm from the Danish Technical University was unable to make this general presentation on AMF and its work on methanol, so I was asked to give this presentation. So IEA has something like 40 different technology collaboration programs. 7 of those are directly or indirectly related to transport. And what this cooperation is about, it's working together and pooling resources and trying to be very objective. So Tim told us when the Methanol Institute was founded, IEA was founded in the aftermath of the first energy crisis in 1974. So IEA has quite good website, so you can have a look at IEA as a whole, and also have a look at the technology collaboration programs, and there is a special part on those related to transport. So the idea here is to pool and leverage knowledge and research capabilities from different countries, and in fact different regions of the world. Exchange of best practices. We try to take into consideration local conditions. All countries are not the same, and there are different ways and incentives and hurdles when you introduce new fuels and new vehicles on the market. AMF does not pursue individual interests, and what we want to be and what we are a kind of international clearing house for unbiased information on various fuel technologies. So actually AMF was started in 1984 as alcohols as motor fuels. So our roots are deeply in alcohol fuels. In 1990, the name changed to alternative motor fuels, basically making space for methane gaseous fuels. And as of 1999, we are advanced motor fuels. When you are working within the IEA technology network, you have to apply for a period of operation, and the current one for AMF is now 2020 to 2024. So we have recently gone through the process of request for extension, and actually we think that AMF is a very active and successful program. There are now 15 countries from all over the world participating in this work, and some 60 odd annexes or projects have been initiated over the years. So actually, to call ourselves advanced motor fuels is a smart way of allowing us to work on basically any fuel. Okay, there are some criteria. So we have defined that advanced motor fuels are fuels that reduce greenhouse gas emissions, improve life cycle efficiency, has high energy efficiency, both in the production of the fuel and the end use of the fuel, has low toxic emissions, enabling fuels for new propulsion systems, and also fuels which contribute to the security of supply. So AMF works on the entire spectrum of fuels, from feedstock through fuel processing, distribution, and finally end use in vehicles. However, we have to state that our focus in most cases is on the end use of the fuel. We of course work close together with other TCPs, and also cooperate within the end-use working party of IEA, and in some cases also with direct interaction, as in the case of Annex 56, which we have conducted in cooperation with the Methanol Institute. So in our new strategic plan covering 2020 to 2024, we have stated a vision for AMF. Advanced motor fuels applicable to all modes of transport significantly contribute to a sustainable society around the globe. So very important is that we can generate unbiased data for decision making on all levels of decision making. And as said, we are able to pool resources and share best practices around the world. So AMF and methanol. I think that methanol is definitely on the radar screen of AMF. Methanol is a versatile energy carrier. We have efficient processing of the fuel. We have multiple feedstock options, both fossil and renewable. There are no carbon-to-carbon bonds, which means that you have practically soot-free combustion with methanol. There are several engine technologies possible based on assist ignition. I guess that Martin will comment on that part. There is potential for high engine efficiency, and in fact, methanol fulfills most of AMF's criteria for advanced fuels. As said, AMF started as an agreement on alcohol fuels, and over the years there has been many projects or annexes including alcohol fuels, meaning that we have had projects where we compare, for example, renewable diesel, gaseous fuels, alcohol fuels, and some of the annexes have been specifically on alcohol fuels. So if we pick some of the newer ones, Annex 44 was research on unregulated pollutant emissions from vehicles fueled on alcohol fuels. Annex 46 was alcohols for compression ignition engines. Annex 54, GDI engines and alcohol fuels. And now the annex we are talking about today, methanol as motor fuels. We are about to end a large project called Heavy Duty Vehicle Evaluation, and this covers diesel, renewable diesel, gaseous fuels, but also ethanol for heavy duty engines. And quite surprisingly, the ethanol engine actually showed the highest efficiency of all the vehicles, all the engine technologies tested. We expect that report to come out early next year sometimes. So we have, as said, 15 countries from all over the globe, from the Americas, from Europe, and from Asia. And there is a large number of research institutes and organizations participating in this work. So whatever we do within AMF has to have an international dimension. So the AMF contacts, which you are free to make contact to, are the chair, as mentioned, Jesper Schramm of DTU in Denmark. We have regional vice chair, Mr. C.B. Lee from Korea, and Mr. Michael Wang from the US. And our secretary, Dina Bakovsky, is in Austria, so she's based in Europe. I was asked to put 2 bullets in the end regarding AMF and methanol. And I would like to conclude by stating that alcohol fuels, including methanol, are an essential part of AMF's legacy. But however, AMF also foresees a role for methanol, and especially renewable methanol, as a future energy carrier in the transport sector. Thank you.
Thank you, Nils-Olof. Next up, we will be having Dr. Franziska Müller-Lange. She's the head of biorefineries department at DBFZ in Germany. So just before we move on to the next presentation, I would just like to remind participants that your questions will be answered at the Q&A session at the end of all the presentations. Do feel free to type in your questions in the questions tab. So without further ado, Franziska, the floor is yours, please.
Yeah, thank you very much. Welcome also from my side. As Niels Olof already mentioned, I would like to show a bit of our results that we elaborated in Annex 56, more from the perspective of methanol supply and the issues especially related to renewable methanol.
Looks like Tim is needed to move the slides.
Nu vil de miste al lyd.
Hi, Franziska. I think you might be muted, so maybe you might want to unmute yourself and start again. Sorry about that.
Okay, so hope that everybody can hear me now. Perfect. So I will start from the beginning. Again, welcome from my side. I would like to give you a short introduction into the market of methanol, on the role of renewable methanol. If you, Tim, could you just go ahead with the next slide would be great, because there's much delay here. Yes, here you can see an insight on the global energy demand with a special focus on the transport sector here given for the year 2018. And you can see that roughly 10 million tons oil equivalent are used for in total, of which 1/3 is coming from transport. And we see that we have a huge increase in the past 30 years of approximately 46%. The role of renewables, as you can see from the small diagram, is quite small at the moment. We have alternatives like natural gas, but even electricity and other fuels, and the role of biofuels and a bit waste in there is just about 3% of the total energy demand in transport. This is covered by renewables today. We all are aware of the huge pressure to reduce GHG emissions and CO2 emissions in transport as well. Here it's even similar, about 25%, which is covered by the transport sector, and here in line with the increasing energy demand, more than 44% increase of CO2 emissions compared to 1990. So especially renewable fuels and also methanol could make quite good contribution to GHG or CO2 emissions, but also to other emissions, as we will highlight right now. Please, the next slide. Yeah, here you see the development of the methanol market as it is in the past years. We show here the capacity and the demand and the use of methanol in the different sectors. You see the mainly part is comes from fuel applications as straight or blended fuel, as intermediate for biodiesel production, MTBE, or like dimethyl ether or methanol to gasoline. And of course also which is a minor role today, but we will have also an example on that, the role of methanol as energy carrier for the fuel cells. You see that the capacity increases quite much in the last years. We have more than 150 million tons on production capacity worldwide available. And yes, there are many different applications of methanol. The main driver we see on the fuel market as a motor fuel is seen in China, where we have more than 100 million vehicles that are using methanol as straight or as a blended fuel. And as we will hear from the others today, there are also some interesting applications in the marine and fuel cell sector as well. But keep in mind, the key message here is methanol as a multi-purpose fuel. Motor fuel application is one part of them. Could you please go ahead? Thank you. Speaking for renewable methanol, we have at the moment less than 1 million tons per year, so it's less than 1% today. So even covering the positive effects of methanol as a fuel from the standard limited emissions, but also from the GHG, we need to increase these capacities right now. There are some nice examples on that. Quite famous are the AMF plant in Canada that are using municipal solid waste via gasification process, which is called like a BTL process and will be continued in Europe as well. Then the quite famous power to X or power to liquid methanol route from Iceland that are using hydropower and geothermal energy. And last but not least, methanol as a fuel recovered from the pulp and paper industry as a byproduct, with the example in Södra in Sweden. We have different technology readiness level. This is important to have it in mind for the supply chain for methanol. The higher the technology readiness level, the higher they are on market availability from the technology side. From biomass, it's depending on the technology and processing up to 7. For e-fuels or power to X, it's 7 to 8 years. As I mentioned already, the key here is to expand also the market for methanol as a motor fuel, to expand the production capacities of renewable methanol, even from biomass, but also from renewable energy. Please go ahead. For the different routes, we in Annex 56, we made an assessment literature base for GHG emissions, because these are important things to have in mind. There we assess different studies that have been reviewed for renewable methanol and also for fossil for comparison. And you see on the right-hand side a comparison for many different technologies and studies. They are mentioned also in the summary report that are available to you. And you also see a huge bandwidth even for the renewable part, but of course also for the fossil ones. You see that we can reduce renewable net methanol, for instance, against the Renewable Energy Directive 2 in Europe from 65 to 90% GHG reductions compared to the fossil reference. And have in mind that the main drivers for that are, in any case, the resources itself. And there especially wood might be interesting, but also different applications that are considering biogas. And of course, the conversion technology. And here we see, especially for the part of power to liquid fuels or e-fuels in the international context, they are much relevant. What are the CO2 coming from, the electricity coming from, etc., etc. Anyhow, the important thing is the GHG reduction potentials show that they can be competitive also with established renewable fuels. For instance, we have in Germany now within a GHG quota average on GHG mitigation of renewable fuels from more than 85%. So these are have to have in mind when we are talking about methanol as a competitor also for other fuels. Please go ahead. Thank you. The same we did for GG, we also did for the production costs. Here even we analyzed different literature-based analysis, normalized them to 2018 and compared them with different price levels, as you can see here. So of course, renewable methanol is like the other renewable fuels, more cost intensive compared to fossil methanol, which is usually made by natural gas and even a bit on coal, but natural gas is the most important resource for that. We see that especially for power-based methanol, we have a wide bandwidth of production costs, and here again, just for information, renewable motor fuels in Europe, some price levels for ethanol as an alcohol, but also for biodiesel and biomethane, which are in that case also competitors for methanol. But anyhow, here you see again that also in that umbrella, methanol could make interesting option for the future as well. Last but not least, please the next slide. It's quite important also to consider what are the prospects of commercialized methanol as fuel. As Niels already mentioned, methanol has a long history with different successes, how to say, in different regions of the world for different applications. And we see, like for other renewable fuels as well, that we have different barriers to be fulfilled on functionality, on scalability, but also on affordability, and last but not least on sustainability, which not just cover GHG mitigation, but also different or several sustainable development goals. They have to be covered or have in mind issues related to the use of methanol as motor fuel in different applications like duty, heavy duty. We will hear about different examples, but also the scalability with regard to infrastructure issues, with regard to supply of affordable amounts of methanol for the market. And then this has to be bring up in line with issues that are related on the strategy side to develop roadmaps, to develop stakeholder and shareholder network from a very early beginning of implementing renewable fuels, together with issues that are related to technology aspects with regard to the vehicle, but also methanol supply, but also regulations. Fuel standards are one example. Legislation to be mentioned, for instance, CO2 regulations for different new fleets, including renewable fuels as well, for instance. Fuel standards related to higher amounts of methanol blending, to mention some examples. But last but not least, which is quite important, and also the IEA, AMF, and especially Methanol Institute works very hard on this, is the part of communication to increase visibility of methanol applications for the transport sector, but also successful demonstrations with the support from all the stakeholders, from the economic, from the NGOs, but also policy side. So supporting elements are strongly needed, not even just on the technology and regulative side, but also on the other hand side. So there are, the next one is my last slide to be concluded with the some of the key messages highlighted here. The others can be read in the summary report. As I mentioned, methanol is a multi-purpose fuel. One has to have this in mind when considering methanol also as a transport fuel. So there are interactions between the different markets and also the competitors, of course. I hope that we could show that there are production costs and GHG reduction potentials that for methanol that could be competitive also with other renewable fuels. I hope that we could show that we can also have an interesting impact for GHG mitigation and transport when increasing production capacities of renewable methanol. For our understanding, this is a key when rolling out new alternatives again, or in some markets for the first time. And for realizing that, supporting elements are quite urgently needed on a strategic, regulatory, technical, but also on the communicative level. So thank you very much for your interest in this presentation. Thank you, Tim, for forwarding.
Thank you, Franziska. I'm sure we will probably get quite a few questions on renewable methanol, so don't zone out too soon yet. Next up, we will have Kim Winter. Kim Winter is from the Danish Technological Institute. He has a 25-year career background in renewable fuels. He is currently also a member of IEA AMF for about 10 years now, and currently chairs or has the role of Chair of Strategy and Technology Subcommittee. For today's presentation, he'll be covering M85, or in other words, 85% level blend of methanol for passenger cars. So Kim, just give me a moment. I will just pass controls over to you very shortly. Okay, Kim, there you go. The floor is yours. Thank you.
Can everybody hear me?
You're good.
I hope so. I hope so. Well, welcome to all of you. I'm going to give you some hands-on results from the Danish group of this AMF project, and what we focused on is mainly M85 for passenger cars. So let's jump right in. There's a little bit of delay on the slide changing. Wow, there it was. So the motivation for us in Denmark to get into this idea of methanol as a new sustainable fuel is that we are an intensely farmed country and we have a large meat production, and of course that produces a certain amount of manure. And we already know that biogas is a very good way of dealing with the manure, and it greatly reduces the natural methane emissions, so it's a very good case in terms of climate. We already know this, and we're already doing this, but the biogas can also be turned into methanol, which is what we did in this project. Now, it's even possible to obtain negative CO2 emissions. Actually, when you read the latest version of the European Renewable Energy Directive, then certain types of digesters can be attributed with a negative CO2 value, which of course just makes the case even better. However, in this study, we did not include negative values. But we already know that that biogas makes a good case, and that biogas can be cleaned into biomethane, and that in turn can be reformed into methanol. But imagine if we could use the CO2 as well. Now I wanted to look to the bottom of this slide. The red arrow is actually excess CO2. About 1/3 of the biogas is actually CO2, which is does not have any immediate value and no immediate use. So we are usually just actually wasting that or venting it to the atmosphere. But what if we could actually use that CO2 and make a sustainable fuel? And that's actually happening at this moment with the so-called PTX technology, or power to X. We have already one demonstration plant in Denmark that is producing enough fuel for about 200 cars, and at least that's a start. Next year they're going to build an even larger one, which should be able to fuel some 14,000 cars. So naturally that seems like a very, very good case. And if we use the entire potential for biogas in Denmark and we convert all the excess CO2, we would have enough fuel for about 1.6 million cars, and that's actually equivalent to the entire fleet of gasoline cars in Denmark. I try and change this. Okay, so if we do that and we try to do the math on CO2, again, we are not going to use negative values because I think that's a little premature. We have not got that certified yet, but we are going to use the values from the old directive, which is for wood methanol default 5 grams of CO2 per megajoule. So naturally, when you do produce a vehicle that costs some CO2 for a gasoline car, it's about 5 to 6 tons of CO2. Then the fuel that you would use during the course of the life of this car would be just under 20 tons of CO2, giving a total of 25 tons. Now, let's compare that to an electric car that's connected to the Danish grid. And the Danish electricity is actually very clean, so electric cars make a very good case. However, producing an electric car yields a little more CO2 than producing an ordinary car, so about 8 to 9 tons. The emissions during driving would then be significantly lower, especially because Denmark has such clean electricity. But the end result would be somewhere around 13, 14 tons. Now, compare that to a car fueled with M85 from biogas. That would, in terms of car manufacturing, be the same as a gasoline car, between 5 and 6 tons. The driving emissions would be about 6 tons, and the total would be just under 12 tons. So you actually see, in terms of CO2, it's quite capable of comparing itself with even electric cars. So I think generally, yes, we have a very good case in terms of CO2 with this technology. I'm gonna move on. So you might ask, if we have all that biogas, why don't we just use that directly? Or why don't you use the hydrogen from the wind power? And why do we want to make methanol? Well, simply it's more feasible for storage and distribution. If we were to use methane, we could do so, but we would require a lot of new fueling stations and also new cars, because current cars on the road do not run on methane. Now, hydrogen would require a whole new grid because we don't have a grid for hydrogen. It would also require new fueling stations and new cars. So in terms of cost and time, it seems that on the short to medium scale, methanol is clearly the fastest option. If, of course, we can get the existing cars to work and the existing fueling stations to work. Now let me talk a little bit about the cars. We've been looking at 2 cars so far. This is the old one, 2008 model. This type of car is actually very popular in Denmark, very small, but it does the job from A to B. It's a Euro 4 emission class, and it will run on pure methanol once it's warm. A cold start is another issue. However, when we use this Artline E85 Flex Fuel kit, it dramatically improves the running, and it improves the NOx emission, not the least. But anyway, once we've driven a few days on the methanol, the check engine light comes on, and when it does that, it's technically not legal to drive the car anymore. So we can't get an MOT on that. So we kind of gave that up and moved to a newer one. This is the new one. This is a 2020 model, a bit same size of car, but a much more modern engine, much more cleaner vehicle. This is a Euro 6, so it meets the highest emission standards that we know of. The engine calibration was done by a race tech company, 2M Technic in Denmark, the company that usually builds race cars, and it runs actually very well. There's no physical changes to the car, only software changes, and we're quite happy with that one. I'm going to show you some results on them. Like first, the fuel economy. This is back to the old car. We can see that in most cases the fuel economy is similar, whether you use a gasoline or an M85. In the WLTP, which is the indoor dyno tests, there seems to be an advantage to methanol, but for now, for the time being, we were not able to replicate that result on the open road, probably because it's colder in Denmark than you have inside a dyno lab. But there may be some benefits that we could gain. Let's have a look at the CO emission, carbon monoxide. Well, that's clearly much lower on M85. There's really no question about it, and we are way below the limit. And with the new vehicle, we are even way below Euro 6 limit. So it's almost well, it's very close to zero actually. So not at all a problem here. Looking at the particulates, well, that's not a problem at all. This Euro limit 5B is actually still the limit for Euro 6. And you can see that we are well below the limits in any case on both methanol and gasoline fuel. So we don't really have any problems here. Now, in terms of NOx, things tend to get a little worse. And before we install the flex fuel kit on the red car, you'd see the two measurements that are actually quite high, up to 2,000 milligrams, and the current limit for new cars is 60 milligrams. So that's quite a bit of way. But as you can see, the use of the flex fuel kit did actually improve things a lot, and we got very close to the values of gasoline, but not quite to the Euro 4 limits. So we have something still that we need to improve. This is just to sum up what happened with the red car. In general, we had, of course, we adjust the air-fuel ratio, as you can see in the table. We get a little extra power, a little extra torque. But in terms of energy, we get pretty much the same. Of course, we get a higher consumption in liters due to the lower energy density of methanol. But the overall efficiency of the car and the engine was constant. The CO2 was the same on both fuels, tailpipe CO2. And the carbon monoxide, much better on methanol, NOx a little bit worse, particulates good in any case. So this is the absolute latest results that we did just last week. And this was actually an attempt on a full Euro 6 emission measurement on the white car. And as you can see, we were actually very close to getting the full certification values. The trip as average was approved, just with a small margin, but the city cycle itself was a fail. So we're gonna have to redo that, of course, and the car is already now back in the 2M workshop to be further optimized for cold start and city driving. And I'm sure in few weeks we will have this perfect result to show you. So just to show you the progress that we made from the standard 108, which was this is in ppm. We started with just over 1,000 ppm on the first trial. Then we put on the flex fuel kit. We got down to 400. Then we got the new car was down to 100 the first try, and the target is about 50. So that's what we are going to try and reach now. And the yellow dots are the gasoline measurements. So what are we going to do next? We're going to make a bigger demonstration program to include 100 cars. They will all be optimized by a 2M technique. We will have the big energy companies distributing the energy. We will have some of the big cities using the cars. We even have a company who makes the tanker vehicles on board, and we get support from the Danish Energy Agency. So all in all, we anticipate a lot from this project. I think we will be running around Christmas, probably, the first cars, and we will have 5 or 6 fueling stations in place. So just a few words on the barriers. Of course, we know that methanol has been used for many decades, maybe even 100 years as a motor fuel. Why is it not used today? Well, first of all, there are such things as exchange agreements. When we distribute fuel all over Europe, there are agreements between the different companies who will buy and store and exchange, and some of them might not want methanol. So that's one reason why there would not be any methanol in, for example, the Danish fuel. Just a few years ago, it would simply not happen. I think actually they did change the agreement now, so now at least it could happen. Second problem is that E10 is actually cheaper. The ethanol, first generation ethanol, is cheaper than biomethanol. So for the time being, it's the cheapest option. It's not the most eco-friendly option, but the first generation is ethanol simply is the cheapest alcohol right now that will do as a that will fulfill the European blending mandate. The problem is that these blending mandates in Europe, they don't actually account for CO2. They just assume that a biofuel is a biofuel, and that's it. So, I mean, if it was calculated on basis on CO2, it would be different. Another problem is in the vehicle industry, the CO2 that comes out of a biofuel is counted as 100% fossil. So the vehicle industry have nothing to gain from making biofuel vehicles because they are considered fossil vehicles, really. So that means, of course, that we don't get any real support from the vehicle OEMs because they have really, at this point, nothing really to gain from supporting this. But we think that through our demonstration programs, we can assure confidence that the methanol blends is safe for vehicles, infrastructure, and that any technical difficulties that we might encounter, they can of course be solved. So that would be all for me. Thanks for watching, and please follow us on LinkedIn.
Thank you, Kim. I know that I said that we'll ask questions at the end, but well, I'm moderator today, so I'm going to indulge a little. I just wanted to bring up a point before I forget when we get into the Q&A session that you drew up in one of your last slides where you said biofuel mandates do not account for actual CO2. And I think that's a really complex question when you're taking into account some of the key legislation at play down here. I mean, I'm assuming one of which will be RED2. Where even if, I mean, biofuels are also affected by intended land use change, etc. Do you have any kind of idea how some kind of harmonization as well as alignment can be made in terms of a policy, in terms of policy to sort of bring in biofuels and CO2 into the same sort of discussion where a solution can be sort of beneficially for both the production of biofuels, but also while taking into account CO2 reductions?
What I know is that this is actually being discussed in the parliament right now, and the government is going to come up with some kind, at least the Danish government is going to come up with some kind of plan for giving a CO2 mandate rather than just a biofuel mandate. And if they come up with a good plan, probably that will spill over to the rest of Europe, and we'll see.
Franziska, maybe you wanted to raise something?
Yes, I just can add something on the that RED II need to be realized in the European member states by next summer next year. There are several let's say proposals how to implement these into national legislation. And what Kim mentioned for Denmark is something what is already in place in Germany, for instance, where we have this GHG quota, and where we will most probably will have in the transposition of RED II a part of which is related to GHG or CO2 emissions. but also with different quotas with minima and maxima, for instance, for high ILUC biofuels or low ILUC biofuels or conventional ones. So this is addressed in the RED II and need to be transformed into the different national legislation. So might be, of course, an interesting opportunity for methanol as well as so-called advanced biofuels, but this is just a European perspective I need to highlight here. Yeah.
Thank you, Francisca. So next on, I would like to move on to our next speaker. I think we'll delve a little deeper when we get into the Q&A session after this. I'm sure our audience will have some questions on this too. So next up, we have Martin Thuner, who holds the position of Vice Dean of the Faculty of Engineering at Lund University. He's going to be speaking to us about high efficiency methanol engines. So Martin, the floor is yours.
So thank you very much. And I would like to acknowledge my colleague Sebastian Verhelst also for input for this presentation. So first, okay, let's hope they stay there, the slides. So I will quickly go over or give you an overview of methanol properties and methanol engines. And methanol has quite some interesting properties as a fuel that enables higher efficiencies compared to the conventional gasoline or diesel fuels. It has a high research octane number that gives increased knock resistance. It has a high burning velocity that can be used for increased expansion in a combustion engine. It has a high heat of vaporization, which gives cooler charge and also lower combustion temperature. There is a high lean burn limit and also a higher EGR tolerance. And it's also a high hydrogen and oxygen to carbon ratio, which is important for the emission formation. And there's a lack of carbon-carbon bonds that was already mentioned and associated with no soot production. And these beneficial properties can be used for increased power of the combustion engine or reduced exhaust heat losses and reduced heat transfer losses that are associated with the efficiency of the engine, and reduced emissions as NOx and also CO2 due to the lower carbon ratio of the fuel. There is more hydrogen energy in methanol, and it can also be produced in a number of sustainable ways that helps further. And no soot, like we already mentioned. When it comes to combustion engines, it's really nothing new with methanol engines and combustion engines. It's been used for a very long time in high power applications. For instance, during the Second World War, when you could almost double the power output of a combustion engine by feeding it with methanol to fly away from your enemy and survive that day. So it's been popular in motorsports applications, and it's also been used in very small applications like model engines, in super big engines for the maritime industry, where the emission performance is especially important, and also used in car engines, E85, M85 engines, just like we saw before. So you can look at the line down here that goes from orange to blue. And if we go on the orange side here, that represents the fuel reactivity. And methanol is just like gasoline, a fuel with low reactivity. It's difficult to ignite it. So you need to have some means to support the ignition of the combustion. And that is typically done with spark ignition. So conventional gasoline engines has been used for methanol for a long time, and they work very well with that fuel. On the other side of this scale, on the blue side over here, we have the diesel combustion. So conventional diesel engines running on diesel. You don't need any assistance to ignite the diesel fuel. You just need to compress so that it's warm enough in the combustion chamber of the engine, and then you put in the fuel. And you can also use methanol for this type of combustion, but you need to modify the methanol fuel with ignition improvers, and that is known as MD95. And I think Päivi will take us through that a bit more in detail. When it comes to research and methanol fuel, we have been working with, for instance, RCCI, reactivity controlled compression ignition. Here you have two different fuels. You use the methanol, which is represented in orange here, and then you have a diesel fuel that kicks off the ignition. So it's sort of a big spark plug, if you like. And you can tailor a bit with lean combustion here to reduce the heat transfer losses. And this sort of strategy is also similar to dual fuel that has been used in the Stena Germanica, which we see down here, which combine the diesel engine with a dual fuel concept. And they did it in a very clever way by having both fuels injected directly through a similar, or for one injector. The partially premixed combustion that we have been working in Lund is a lean combustion strategy. You don't have any spark plug or ignition assistance here. You use the compression, but in a slightly different way. And you can also combine this with spark ignition, and then you get a lean burn DISI engine. And DISI engines is also used currently for higher end car applications with gasoline, but not in lean burn mode. Can you bring the slide forward, please? Thank you very much. So if we start by looking at methanol in conventional gasoline engines, the DISI engine that I was just talking about, and there are a number of these type of engines on the market right now. In this case, it's a Hyundai engine. And just recalibrating it slightly so it was possible to use methanol, we could see that the efficiency was improving quite a lot actually, and without any optimization really towards methanol. So a stock gasoline engine can be used, well, adapted for methanol with higher efficiency. So it's pretty remarkable, I would say. And you could go even further if you could optimize this particular engine. One way to go even further is to turbocharge the engine, and this is like the engine to the right here, which is a Volvo engine, and then we can see even higher efficiency by using methanol compared to gasoline. Next slide. Methanol can also be applied in diesel engines, even though it's a bit more complicated. And this is where we have been using the partially premixed combustion strategy. So the figure you see here is a representation of the diesel engine, and it has about 45% brake efficiency. It's a good truck diesel engine and calibrated and optimized for diesel operation. With PPC, we have tried that type of engine with gasoline fuel, which you can see down here, and we get a slightly higher efficiency, but we especially benefit on the emissions, so lower soot, lower NOx by this strategy. Now, if we take methanol into the same engine system, we are improving the efficiency quite dramatically here, but it's still not optimized for methanol. It's still a diesel engine that we fuel with methanol. If we do some optimization here by increasing the compression ratio, we have improved efficiency even further, and the emissions now are way much lower than for the conventional diesel engine running on diesel fuel. So a lot of potential with this concept, we think. Next slide, please. And to give you an overview of how we could develop the concepts further is that we have on the left axis here, we have the pollutant emissions, and we have efficiency on the x-axis down here. We have the gasoline engine in green to the left, and to the upper we have the diesel engine. So standard calibrations, and you can see the diesel engine is more efficient, but not as clean as the gasoline engine. To improve the efficiency of the gasoline engine, we need to do something about the NOx. This is a big problem for gasoline engines. And we can use something called octane on demand. We could fuel a little bit of methanol into the engine, and that improves the efficiency. If we increase the amount of methanol in the fuel, in the gasoline fuel, we are improving efficiency even further. And if we could then calibrate and build dedicated methanol engine with a correct compression ratio, more downsized, and using high EGR or dilution ratios, we are improving efficiency to a level that is actually higher than a diesel engine. And you can also work with waste heat recovery to take even further steps from that. Going from a diesel engine base, the blue box or circle up here. You can do the dual fuel strategy like you have in the Wärtsilä engine on board the Stena Germanica. So dual fuel combustion, you have reduced emissions, so you can especially reduce the emissions. That's the benefit there. And if you make a compression ignition engine that is dedicated for methanol combustion like PPC, then you don't get any soot at all. You're using 100% methanol fuel, and you can focus on reducing the other emissions and improve efficiency even further. So we see a large potential for improved efficiency and reduced emissions by shifting fuel to methanol. Next slide, please. And this figure, and this is just a representation of what we have achieved in the laboratory with PPC in a diesel engine base. We can reach Euro 6 compliant emissions without any after treatment. And that is, I think, quite remarkable. By changing a fuel, you can get this very, very good performance on emissions. Next slide, please. There is currently a very fast development of internal combustion engines for gasoline and diesel, of course, because those are the fuels that are available at large scale in the world. So huge developments there. And this figure represents the different ways to improve efficiency further. So we have the advanced engine concepts here, HCCI, PPC, and RCCI that I have explained a little bit about. And from that, you can also apply waste heat recovery or waste energy recovery for even further efficiencies and maybe reaching 60% efficiency in the future. Next slide, please. That one, thank you. And when it comes to car engines or more conventional type gasoline engines, they are approaching 50% efficiency. One example is the SIP program in Japan, where high-octane gasoline engines are surpassing the potential for high-efficiency diesel engines, which is quite remarkable, really. And the strategy for those engines are to run them ultra-lean and with assisted compression ignition as critical factors. And that brings us closer to what is known as low-temperature combustion, similar to PPC strategies. Next slide, please. Also for truck engines, there's a very fast development and efficiency improvement. In the USA, they have been working with the super truck programs, and we have 4 different figures over here just representing the paths for improved efficiency from Cummins to the upper left, Volvo on the upper right, Daimler-Benz on the lower left, and then Navistar. So 4 different manufacturers showing the way on how to reach these very high efficiencies. And that is partly related to combustion strategies and also waste heat recovery systems for these combustion engines. Next slide, please. In Lund, we're working together with Volvo on a new advanced concept called the double compression expander engine. And that is separating different cylinders for different tasks. And by that, we can reduce the friction and heat losses in a quite dramatic way. And according to our simulations, we reach about 56% efficiency, or the potential is there at least. And we have built a prototype now that we are doing our initial experiments to see if we can actually reach those in reality as well. Next slide, please. But even though we have all this tremendous development on gasoline and diesel engines, the beneficial properties from the methanol fuel still remains. We have the increased out-ignition resistance, we have the lean limit extension, and low adiabatic flame temperature, all features that are relevant for the modern or advanced combustion engines that we see coming. So I think we will see this benefit on efficiency also in the future compared to gasoline and diesel. So maybe we could see a 60% efficient DCEE engine on methanol in a couple of years. I hope so. Next slide, please. So what applications can we then have for these high efficiency engines and methanol engines? And the figure to the right here is just showing that there are a number of groups in the world working with methanol engine applications, so we're not alone at all. Next, please. With consideration to that there is not so much of fueling stations with methanol available today, I think the first steps for use of high efficiency methanol engines should be within captive fleets, especially on sectors where there's a high energy consumption. So the maritime sector is one important sector to get started with methanol, and they have already started with methanol due to the beneficial properties in terms of emissions. But it's also important to remember that methanol as a fuel has a much reduced risk in terms when there would be a fuel spillage compared to gasoline and diesel. And that is also a quite nice feature if you consider fuels for the agriculture sector or the forestry sector, which I think would be the next step in captive fleets for high efficiency methanol engines, high energy consumption, and very important, of course, to have that as a sustainable sector. Other sectors that are consuming a lot of energy is the long haulage sector, where it would make sense to also have methanol engines. Next slide, please. Methanol is currently accepted for a drop-in about 3% in regular gasoline, according to the EN 228 gasoline standard. And that will, of course, lead to, I mean, for the production of methanol, that is huge amounts, only 3% still. The next step is going for dedicated or flex fuel vehicles using high proportions of methanol. One way is to use the gasoline methanol concept, the GEM concept. And you can see on the figure to the right here, which fractions or blends between ethanol, gasoline, and methanol you need to use to comply with the control system of an E85 car. And it's not surprising that methanol actually works very well with these E85 cars, because the whole technology for E85 originates from M85 cars. When it comes to hybrid applications, I cannot see any reason why it shouldn't be run on renewables. And one example of an alcohol hybrid is the concept that Toyota has presented on the Brazilian market running on E100. And I think it's a fairly low technological step to make that methanol compliant as well. On a couple of emerging markets, we will see that already see that there's a large demand for low-cost cars, and methanol engines can be produced at low cost but with still high efficiency, naturally aspirated, rather simple engines for low-cost cars. And I think that's a good application. Next slide, please. So we go to some market penetration considerations. Next slide, please. And we need to know the challenge. What are we facing really here? And just to give an idea of the scales we are facing. So the upper graph here shows the global production of oil in the world 2019, about 6 billion tons. And the methanol production capacity in the world is the orange dot down here. So, I mean, there's such a vast amount of energy that we need to come up with to replace the oil. Looking at the number of vehicles that are allowed to use with high, or could be used with high fractions of methanol compared to the 1.4 billion gasoline and diesel cars or vehicles we have in the world is also extremely small. And according to a couple of reports, we are facing a doubling of transportation in the world by 2050 compared to 2010. So how are we going to replace the oil then? I mean, it's a huge amount of energy that we need to come up with that are sustainable. Next slide, please. So phasing out 6 billion tons of oil annually is not an easy task. There's a number of different ways that can be employed to realize this goal. And unfortunately, the debate is often polarized and saying that this is not good and this is not good and so forth. But I think we need to use many of them to realize this very ambitious goal. So starting with electric drive on renewable electricity, that is extremely important, of course, but it's not enough. And if you want to have the details, you should read the IEA 2018 report on future is electric. The main message from that report is that we need to phase out the coal-based production of electricity first before moving further on electrification. HVO is another popular renewable fuel, works great on diesel engines, but it might be prioritized for aviation because it's certified for that in some applications. Biomethane, very important, but probably at too small scale. Ethanol, yes, great, works well with methanol, but not enough on its own, and the same goes for biodiesel. When we come to electrohydrogen and electromethane, now we have scalability, but these are energy gases, so they are maybe not that practical for vehicle applications. Then maybe electromethanol and also the biomethanol, we know that they have great potential, but not even them are all will solve this phasing out of oil on their own. So we need more than that. Next slide, please. We did a similar or a study in our group that ended up with very similar results to what Kim showed, and I'm happy that we have a match on the figures here. So we did simulation studies, quite advanced such, on 200,000 kilometers of driving in the WLTP cycles with different fuels and drivetrain combinations. And the left figure here shows the life cycle CO2 from a diesel car, on the left, the grayish one, and then biomethanol, the green one, and Swedish electricity electric car on the blue one. And we can see that of those three, the biomethanol seems to have the best potential to reduce CO2. But we took it a further step, and we wanted to understand which is the most cost-effective way to reduce CO2 from transportation, because we have limited resources and we should obviously use the most cost-effective solutions first. So we looked at the production costs of the vehicles, the fuels, and the use of them, and removed all taxes and subventions. So it's a sort of a societal cost for reducing CO2. And we compared with a number of different fuels, but in this figure here, you can see the biomethanol on the left in green and electric car and Swedish electricity on the right. And that shows that biomethanol cars seems to have a very good case. We should remember, of course, that the scenarios are quickly changing. Electrification is becoming more cost effective and so forth, but it's clearly a good case for biomethanol as well. Next slide, please. So how about barriers from our perspective? Well, we think that there are a few reasons why methanol should not become an important sustainable fuel. It is scalable, affordable, and largely functional. The engines are based on simple and abundant materials, so that should not be a showstopper. The potential challenges for large-scale market penetration of methanol engines are more related to lack of relevant regulations. We heard a bit about that before. Could be also a massive breakthrough on fast charging and new types of battery for electric vehicles, reducing the cost and so forth. Or strong cost reduction of fuel cells, making fuel cell vehicles a competitive alternative. And also a stronger demand for renewable methanol on other sectors for green chemicals and so forth. Next slide, please. So my final slide here, the needs for large-scale introduction of high-efficiency methanol engines. And we needed legislation, so that is holistic, life cycle assessment based, that provide meaning and long-term stability for the markets for sustainable fuels. The current tailpipe-based regulations are simply just foolish and with double counting and a lot of meaningless ways and delaying important measures against climate change, as I see it. Obviously, like I showed, the challenge is enormous. So the availability of methanol and vehicles requires an enormous scaling up of the production and distribution and so forth. On the technical side, we see that we need especially robust fueling system and especially fuel injectors with proof of long-term durability. There's a need for fuel standards for neat methanol and various blends of methanol. For the neat methanol, we don't need chemical grade. I cannot believe that. So it should be a lower cost methanol as I see it. But we need a standard to define that. There will be certainly a lot of certification work for engine and vehicle manufacturers. Introducing a new fuel is always a large task for them. And we need research and development into the high efficiency future methanol and dedicated methanol engines. So thank you.
Thank you, Martin. You raised up a point there which I thought was quite interesting, but I think we'll use it to kickstart Q&A later, and I'll address it to all presenters today, just to make things a little interesting. Well, so next up, the last speaker that we have today is Päivi Aako-Saksa. She is the principal research scientist at VTT, and she researches fuels and exhaust emissions. She's also the research team leader of VTT emission control team. So without further ado, what I'll do is, Päivi, if you don't mind, I'll control the slides just to ease the transition for today.
Yes. Thank you very much. So I'm going to tell you about marine methanol and going through why marine methanol is needed, pathways to methanol, then some examples of marine engines and project examples, and then conclusions. So next slide, please. So why marine methanol is needed and how this is different from the other sectors? Aviation and maritime has something in common, and that is the dependence on liquid fuels. So when you are flying, it's very difficult if you have some problems with or refuel gas fuels which need a lot of space, and the same applies to overseas shipping. So liquid fuel is a good fuel for maritime. And for long time in history, ships have been traveling with residual fuel, which is actually a waste from refineries. But now this has been changing very rapidly. The International Maritime Organization, the IMO, has already been setting quite tight regulations to reduce emissions from shipping. And first, these regulations applied sulfur emissions, NOx, nitrogen oxides. And today we are talking about black carbon emissions and methane emissions, which is quite much related to LNG use in shipping. But the new thing now is that global warming burden of shipping also needs to be reduced. And the IMO has announced of a strategy to reduce sector's carbon dioxide emissions by 50% by 2050. And this is a big sectoral challenge, actually even bigger than in any other transport sector, because of the long history with affordable, cheapest fuel that can exist. Next slide, please. Maritime fuels are not used as much as road transport fuels, for instance, but anyhow, the volume is significant. So annually, more than 260 million tons of maritime fuels are used, and only a very small share of that is even LNG. Most of that is still residual fuel. And although the global sulfur limit that was set in 2020, a lot of residual fuel is still blended with distillate to achieve the 0.5% sulfur limit. Okay, and then if we go to the IMO strategy to achieve 50% greenhouse gas emission cut, we need at least more than 130 megatons of clean marine fuels in 2050. That is about the same volume as methanol is produced or can be produced today, but methanol is of course used today for other purposes, but this volume of sector is not as high as volume of fuels in road sector. Next slide, please. And when looking at the fuels, this perspective was already shown to go different synthetic routes from feedstocks to different type of fuels. So it is quite important to notice and understand that when you produce synthetic fuels, you can really choose which is the end product, which is the molecule. You can use electricity through power to X route via hydrogen or biomass via gasification or waste or fossil fuels, and you can end up in gases or methanol or diesel type molecules even. And all of these conversion pathways have differences, but it is possible to do this kind of choices, to choose what kind of molecule you want to have. And actually, when compared to the huge step from cheap fossil fuels to using renewable hydrogen for fuel production, the differences between molecules are smaller. And then this slide illustrates that almost all of these molecules, when used in internal combustion engine and when combined with the efficient emission control technologies, can give very low exhaust emissions. So these can be approximately zero emission engines as concerns tailpipe emissions. And in addition, depending on upstream emissions, well to tank emissions, these can be also climate beneficial for climate. Next slide, please. This is the pathway from the point of view of synthesis, but we have a limited time, so next slide, please. I don't go into this. How do we see maritime fuel pool in 2050? For sure, there will be fossil fuels. And LNG is one of the alternative fuels that is going to be used. Most probably we don't have any more HFO type of residual fuel as it is. But then the big question mark is like climate neutral fuels. Which are those? They are going to be some 50% of the pool, and methanol is one of option. Next slide, please. If it's from renewable sources. And here is one scenario of transport fuel mix. And the brown bar or part of bar represents fossil oil products. And this concerns Europe, but interestingly, all the alternative scenarios end up in the situation where the energy consumption of transport sector reduces a lot. So then if cars will be electrified to larger extent, then there will be liquid fuels. And the question is who uses them. So aviation and shipping sectors will be important in the demand perspective even then, and the mix might be very, how to say, colorful. Next slide, please. Okay, and then if we look at the marine engines and this sector as whole, most of the marine fuels are used in large, slow-speed diesel engines, which are totally different from those engines that are used in cars or trucks. And then also the medium-speed diesel engines are different. These engines can be tens of megawatts or 100 or more megawatts, and high-speed diesel engines are used only in smaller vessels. And engines for large marine engines are available from two important manufacturers. So both Wärtsilä and MAN have methanol engines available on market. And Wärtsilä engine is a retrofit engine concept, whereas MAN engine is used for new builds. And as Martin told, efficiency can be really high when using methanol as engine fuel, and that is important, especially in marine sector, and some challenges are lower as they are using constant speeds compared to road transport. Next slide, please. And here you can see this Stena Germanica, and maybe I don't go in too much details, as Martin already showed very nicely the engine combustion concepts and so on. So we can move on to the next slide. This is an example of the studies that were carried out at VTT in 2015. So this was the gas diesel concept which is actually used in Stena Germanica. And NOx emissions already achieved in the first experiments were really low tier 2. And now one pathway is to study whether you could achieve tier 3 by blending water in methanol. And particulate matter emissions are low, as well as formaldehyde and other emissions. And after this, with more development, even less emissions are emitted. Next slide, please. And as Martin already told, there is one special concept that is used in commercial Scania alcohol engines on market for ethanol fuel. So ethanol with ignition improver additive. And in one project we studied, or actually two projects, in AMF project, and then in so-called Summit project, we studied possibility to use methanol with ignition improver additive in this kind of engine. And now the Scania and MAN engines are large diesel engines, but this is a truck engine. So this could be a potential concept for smaller vessels. This blend was burning very well, and emissions were really low. Some particle type of material was detected, which was originating from ignition improver additives, but can be removed easily by oxidation catalyst that belongs to this engine, Scania engine concept. So next slide, please. The emissions were studied in a literature study within one project. And so if you are interested in emissions from shipping, in this report you can find results. And here you can see black carbon emissions when using fossil fuels, biofuels, methanol, and natural gas. So methanol engines emit very low black carbon emissions, which is a very good feature, as ships can bring soot in the Arctic and Antarctic regions where it is very harmful for climate. Okay, next slide, please. And now I have here a few slides of some maritime projects where marine methanol has been studied. One of these projects was Summit, and it was looking at smaller vessels, a possibility to use methanol in tolls, how to convert road ferry for methanol, and whole supply chains of renewable methanol. Next slide, please. A lot of this kind of projects have been carried out in Sweden, and this project was a collaborative project between Sweden and Finland, and you can find a lot of results of these demonstrations and other case studies. Next slide, please. A new project that has started in Sweden. I think that Martin could tell more about this. It's Fast Water, which studies marine engine from different perspectives. Finnish organizations are not involved in this project, but looking forward to the results. And next slide, please. This is an example of project in Germany where methanol is used in fuel cells. So the nice feature of methanol is that it can be used both in engine fuel and fuels in fuel cells. So you could think that you could even combine the combustion engine for methanol and also fuel cells, especially in maritime. This is a quite interesting combination, as you could use fuel cells as here as a range extender, or then to produce electricity for ship. Next slide, please. And in Aalto University in Finland, development work on engine concepts is ongoing. This project was SunFuels project, where Aalto University was developing a dual fuel engine for methanol, and observed that early fuel injection has advantages for methanol combustion, and emissions reduced, and also combustion stability improved. Next slide, please. So all in all, methanol features for maritime are very positive in many respects. Methanol, even though it has a lower energy content than diesel, it is a liquid fuel, and the energy content is not that much lower that the ships couldn't bear it. And in addition, methanol can be placed in the double bottom of ship, which saves space. And a good point is that methanol is already used as fuels, and it is a bulk chemical that is transported by ships. And methanol can be very climate friendly in a way that its greenhouse gas emissions can be low depending on its origin. and there are already engines on market. Emissions are low, and high efficiency engines can be manufactured, and it is actually safer than gasoline in a way that it is biodegradable, so that for maritime environment it is quite safe. Then there are also adverse points, like it is low heating value, then safety issues, it is toxic for humans, and then formaldehyde emissions could be possible, but in these steady state running conditions, we have not seen high formaldehyde emissions, and these are to be typical for marine engines. And then materials need consideration, but it is known what kind of materials are needed for methanol, and methanol is not soluble in diesel, so pilot injection is used if methanol diesel concepts are designed. Next slide, please. So as a conclusion, renewable methanol offers potential to reduce both climate burden and health risks of shipping. And the main points are that it is liquid and can have low greenhouse gas emissions as well as tailpipe emissions, and it can be used both in internal combustion engines and fuel cells. But of course, for renewable and sustainable fuels, the main hurdle is how to increase the production and how to do it fast. Thank you.
Thank you, Päivi. I see that we are running a little over time, but I do understand that we do have most of our participants still on board. So if you don't mind, presenters, I'll keep you around for a little while so we can address some of the questions that were raised. But before we go into that, I want to go back to what Martin was bringing up, and I think it also ties in with a point that Päivi brought up, which was there's going to be a doubling of transportation in the future, not a doubling, but a 50% increase in transportation in the future. But then we see in like European scenarios, there is a decrease in energy consumption in the transport sector for different scenarios in Europe. So I'm assuming, of course, that decrease can be due to, for example, increase in energy efficiencies, but also in general, a better organization of our transport sector to include probably more shared transport, carpooling, etc., or other solutions where energy consumption can be lower. So, I mean, if I tie these two together, the assumption of the argument I'm going to put out there would be that this significant increase in transportation demand would likely happen in the developing world. But do feel free to tell me that I'm wrong, but because this is just an assumption that I'm making down here. But of course, we do know in developing countries like China and India, the transport sector is poised to grow quite significantly in the next couple of years or over the next mid to short term, especially when you see a growing middle class, where there's a growing need for a vehicle demand. So in these developing countries, and this question is open to all presenters, what do you think sustainable solutions, for example, methanol or even biodiesel or anything else in the market, even bioethanol, would play in sort of maybe leapfrogging those economies to a more sustainable state of transport in their own countries, because they are able to sort of circumvent some of the baggage that we have right now in developed countries, where we have a lot of already gasoline and diesel cars or vehicles on the road. So the question is open to anybody. I'd be happy. Anybody feel free to jump in and probably give your take on this one.
This is Niels Olof. One feature of AMF is that we are looking at things really in a global perspective and trying to understand the differences between markets. we understand that there is a great increase in the demand in transport in many parts of the world, and then if you think about very crowded cities in some Asian countries, I think that actually regulated or toxic emissions are the main problem. So you have less sophisticated vehicles, low quality after treatment system, low quality fuels. There you have to do something to make it possible for people to breathe. Then I think in such circumstances, unfortunately, greenhouse gas emissions are a kind of second priority. But then if you think about Europe, I think that the whole transport system is in Europe it's actually how do you say it's kind of blocked. If you look at the motorways in Europe, there are trucks after trucks after trucks. So you have to think about the whole transport system in a way, and hope that those countries in development do not repeat all the mistakes that have been done in other countries, like in Europe, because congestion is in Central Europe, it's a problem and so forth. There are so many levels to think about when thinking about transport.
Thanks, Niels Olof. Yeah, I think it's quite a complex question, and I think if we had to answer that, we'd be sitting here for another 2 hours. But so I just want to go into some of the questions that were given, were posed to our presenters today, and I think the first one would be for Kim. But I think this question can also be answered by Franziska. But I think maybe let's have Kim go first, and Franziska will hear your thoughts about it after. So the question from the audience was, I have heard different claims on carbon neutral versus carbon negative for methanol production using carbon capture. Is there a consensus or industry standard describes how methanol production should be labeled, or is it based on the downstream application?
It's not based on the downstream application. It's upstream, of course, but there are so many sources of methanol that you couldn't put them all in one bucket. There would be so many pathways that it's very complicated.
May I add something on that? I think there are different issues of system boundaries to be considered for the operational modes and in the different regions. Speaking for Europe, the RED2 standard or method related to that will be binding. There are lots of open questions regarding counting of different CO2 sources in that. There we will have or we will expect delegated acts by beginning of next year. So I think there are two perspectives. One is related to the technologies, up and downstreaming, and the other one is about accounting within RED2 systems, CO2 fleet regulations, but also in differences with the, speaking for Europe, with the emission trading system. So there are different perspectives on that.
Thank you, Franziska. The next question would be to Martin, but I think Kim, you also slightly covered this, so do feel free to jump in if you have any other thoughts. And this really is about the question of OEM involvement. So actually, it does not even pertain to any kind of single form of transport that we've been talking about today. So it can be passenger cars, it can be heavy-duty trucks, it can be marine vessels. So what is the sort of reluctance from your experience that you face with OEMs not coming on board with some of the projects that you have conducted in the past, or are conducting right now in the present?
I think it's partly a lack of long-term regulations that makes it, a market they could depend on. I mean, it's a huge effort for an OEM to introduce a new fuel and a new engines or drive systems for that. And if they cannot see that there's or a risk for regulations changing again in 3-4 years time, that investment could come to nothing, and no one can risk that. And it's a huge thing only to certify engines, like I mentioned before. So it's a very hard thing to do. So they would need clear regulations, and if we could get some global regulations, that would be great. I mean, because it's too scattered in many ways.
Nils Olof?
Actually, Kim, did you want to respond first?
No, thanks. No, go ahead.
Okay, looking at Europe, the CO2 legislation for passenger cars, vans, and heavy-duty trucks, all based on tailpipe CO2. Actually, the vehicle manufacturers are so busy developing electric vehicles to meet those average targets in the different vehicles segments. So they are totally tied up. And what would be needed would be a European, or actually most preferably a global system, how to take into account renewable fuels. As stated previously, there are no incentives whatsoever today for an auto manufacturer to make for Europe and for example an FFV vehicle. And it's ridiculous because when a manufacturer is producing an FFV, the added cost for that vehicle is less than $200 or euros. So we, in a way, we have blocked with a certain type of legislation and ruling. We have blocked the possibility for renewable fuels to really enter the scene. And we were discussing about what AMF could undertake in the future. One idea would to look globally at regulations related to taking CO2 into account. Either or the current system is tailpipe only, but we should have a better system, well-to-wheel perspective and so forth. So I think it could be beneficial if AMF could have a look at this globally and can come up with recommendations.
I see, Martin, you might have a point to make.
I just wanted to add that you asked the question from a point of that the OEMs would be reluctant, but I don't feel they are reluctant. At least the people I talk with in OEM industry, they're not reluctant. They are lacking the regulations.
Yeah, well, I guess all our experiences are slightly different. I mean, from the methanol industry, the OEMs are slightly. I mean, they do pose some resistance at some times, and I think it's largely understandable due to the fact that, like, you know, they might have to retool their manufacturing lines, and also it's a new fuel that they've not used before. They would have to do their own research and testing, right, and just rely on data that's publicly available. But definitely these are some of the challenges that we do need to address, I guess, moving forward into the future. And I don't think it pertains only to methanol. I think every new fuel that will come into the market that will try to serve the energy demands of the future will go through the same sort of challenges with the existing OEMs in the market. So the next question is for Päivi, and that's really for about aviation. I do have my thoughts on this, but I guess let me ask you about it. So the aviation industry is facing a turnaround with respect to emissions, and hydrogen is the preferred fuel for long term. Do you think methanol has potential to be a fuel in the aviation industry for passenger aircrafts?
That was a quite difficult question. Actually, I think that shipping is maybe the first one to tackle this or to adopt methanol as one of the fuels in the fuel mix. So in the aviation, the regulations are very tight, and they have big challenges to build up new regulations for new fuels. So at least this step is a little bit smaller when going to maritime than when going to aviation. But of course, don't know what happens in the long term in aviation.
Yeah, I think I mean I'll just probably give my thoughts on it, and if I'm not wrong, but I mean somebody do correct me if I'm wrong, because it's been a while since I did work on aviation. But the aviation under the International Civil Aviation Organization does not have mandates for absolute emission reductions, but more of improving the energy efficiency of aircrafts that they are in the market. I believe so. So I mean also that there is not really a real push as compared to the maritime industry to move. But Franziska, please do jump in on that.
May I add some points on that, as this might be a quite German discussion at the moment, increasingly also for Europe, that not methanol as fuel itself is considered as a renewable or a sustainable aviation fuel to be counted within ETS or CORSIA, but even with regard to the e-fuel topic, that the methanol to synthetic paraffinic kerosene route is discussed as one further option that of course needs to fulfill all the ASTM process to be accounted for, but this is really intensively discussed in many different projects. So it's not the alcohol itself, but even as like methanol to gasoline as an intermediate for that.
Thank you, Franziska. So actually, next up, I would like to post the last question to Päivi. And Franziska, don't mind me if I'm not giving you as much time during the Q&A, but I saw that you were quite diligent with answering the questions. So thank you for helping my job be a bit easier. But the question here is, methanol is known to reduce NOx significantly in engines in the maritime sector. I'm not sure if this considers the case where water is emulsified, but that was not specified. But carrying on, and this was discussed in Martin's presentation as a positive quality of methanol as a fuel. So surprised to see NOx increases in the M85 pilot. Why is that the case, or what's the inconsistency? Actually, I'm so sorry, Päivi, that's not a question for you. That's a question for Kim, actually. Sorry.
Oh, could you repeat that one, please?
Sure, no worries. Yeah, so the question is basically there is an inconsistency between whether methanol can be used to reduce NOx when used in ICE.
Oh, yeah, sure. Okay, well, this is clearly from the engine out point of view, there would be a reduction, but going through the three-way catalysts, that would require oxygen-free environments. And since the methanol contains oxygen, we kind of have a tendency for increased oxygen in the catalyst. So it's the problem is on the catalyst, not the engine.
Thanks, Kim. So I see that we are well close to 28 minutes over time. So I do really not want to take up the time of my speakers and the audience anymore. I would like to thank my speakers for taking the time to present your work today, as well as the audience for taking the time to hear about the results that were written about in the AMF Annex 56. We do have a list of your questions that you have posed today. If you're not able to answer your questions, do feel free to get in touch with the AMF Secretariat or our presenters if you have their contact details. If not, do feel free to reach out to me, and I'll be happy to direct you to our presenters. So once again, thank you everybody for joining the webinar today. But most importantly, do not forget to download the AMF Annex 56, which can be done in the drop-down menu on your control panel, which says handouts. If not, you can also go to the AMF website where you'll be able to download the Annex 56 as well as other annexes. If you have any questions about that, do feel free to reach out to me. So thank you everybody once again, and have a good day.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.